The third of our 6 application models in this series of videos is on set covering. The template for the textbook example is again contained within the reading subfolder of the 05 underscore integer underscore OPT folder. Okay, although I'm not going to go through the 8 chapter 15 exercises in either videos or classes, there are great examples you should do on your own as part of your chapter readings. So, in the textbook, the Anderson Village must decide where to locate at most 3 fire stations so that each of the 8 districts or neighborhoods in the village are reachable within 8 minutes from at least one of the stations. Okay, this is a standard set covering problem where a subset of a given set of locations must be selected in order to cover, in some sense, all of the other locations, often by placing the restriction on the maximum number of service locations and possibly other constraints. In this example, the first thing to note is that for each location, there are some that can be reached within the required time frame and others that cannot. So the possible assignment matrix in this model is calculated based on the given travel times and the required response time. The objective is to minimize the total number of stations that can cover all of the districts within the required response time. The decision variables are restricted to binary values 0 and 1. The model is analyzed by changing the minimum response times from 5 to 10 minutes in increments of a minute to see the effect on fire station location selection. Okay, so all this is done in this village fire station.xlx file. So please see pages 527 through 529 for more details on all of this. Our own example of set covering is similar, although a slightly more complex problem. Here, in addition to the decision variables for the subset of locations that will become service centers, the entire customer assignment matrix is also treated as a set of decision variables that will optimally assign customers to selected service centers. These assignments have to be unique. In other words, the sum of each row in the customer assignment matrix must be exactly 1. You will see that the total distance is calculated based on the number of trips and is going to be multiplied by the sum product of the appropriate row in the distance matrix with the appropriate row in the customer assignment matrix, and then in the process of that divided by 1000 to get the number in thousands of miles. All right, so let's go and switch to the Lect5 set covering Excel file, which is right here, to show the number of service centers is budgeted to be 3 among the 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, with the distance symmetric matrix given here with obviously zeros on the diagonal, and then also based on the historical records, a number of annual trips. So for example, 885 is number of trips into Boston from Chicago, Dallas, Denver, and wherever else. 760 is number of trips into Chicago, and so forth. Okay, so you can see obviously some have more, some have less trips, but it's generally relatively well balanced, in terms of number of trips. So the decisions down towards the bottoms, right, towards the bottom, are both the decision on where to locate among these 11 cities the service locations, and also which customer or which city to assign to which service location. Okay, these assignments have to be unique, so the sum, as I said before, of the zeros and ones in a single row has to be exactly 1, not less, not more. Okay, and then the total distance will be covered, okay, based on which service center services this particular customer in each one of these rows, right? And then multiplied by the number of trips for that particular the particular incoming location, which are these numbers given the margin of the data matrix at the top. Okay, these are all going to be added up, right? And then we're going to minimize the green cell, which is the total distance over the entire year, right, for all these combinations, by changing the service center assignments as well as the customer assignments over here while maintaining the unique assignment constraint. And you'll see that there's other constraints as well. So let's start by let's start by selecting um, certain locations. Let's say, how about the ones that have number of trips going into them, just to start with. So one will be Dallas, right here. Another might be, remember we have to have a 3 at the most, which will add up here. So how about, what is this, New York, and then let's say San Francisco, I guess would be the third one, which I believe is not, oh, it is the optimal solution already. So yeah, it's going to be a little bit of a letdown in that sense, but we'll delete the solution to begin with, and then we will rerun it and see we get the same thing. So the rest are not going to be, oops, the rest are not going to be selected for service center locations. Okay. Secondly, right, let's select for each of the 11 cities, right, which city should it be serviced with. So for example, Boston should probably be serviced by New York. Okay, so Boston should be serviced by New York. Okay, so the rest of the entries in the Boston row must be 0. Okay, so Boston is serviced from New York only. Cannot be serviced from Denver. I'm sorry, Dallas as well. Obviously, San Francisco, right? Doesn't make sense either. So then the sum of this row is exactly 1. And this has to be the case for all the rest of them. Okay, so this has to be the case for all the rest of them. And I'm not going to do them. Obviously, I'm going to let the solver do the work. So I'm going to then just do the formulas, which is the unique assignments going down, which of course now they're all going to be 0. Okay, and then I'm going to demonstrate a calculation of the total distance, right, which is number of trips times essentially the sum product, okay, of the customer assignment, right, with the appropriate row in the distance matrix. Okay, so that essentially will take these 213 miles from, this will essentially take the 213 miles from New York to Boston, and multiply by number of trips. Okay, and then we said we're going to divide by 1,000 just to avoid huge numbers to get the numbers in thousands of miles. So 189,000 miles is an interpretation of that number. Okay, and then it goes down to the bottom. Again, just making sure last row, whichever service center, covers Seattle, and it probably should be San Francisco. Let's put the 1 down here, and the rest are 0. We'll then get that number of miles between Seattle and San Francisco multiplied by number of trips, and to get about a half a million, I guess, 500,000 miles. Okay, we'll save that at this point, and then we'll start talking about a solver. So the next thing to sort of discuss is the probably most difficult constraint. Oh, I forgot. Did I have the number of? I added up these to be exactly 3. Okay, so the most difficult constraint is the 11 restrictions on each customer row. Okay, so the customer assignment row has to be less than, so each of these customer assignment rows has to be less than or equal to each of these service center rows, right? These constraints are necessary to force the assignment of customers to selected service locations, including the selection of the service locations itself. Okay, so let's set up the solver first and run it, and then I'll try to explain that constraint later on as well. So let's go to the solver, okay, which is a little bit more elaborate because of these constraints, and we'll start with the objective, which I don't have yet. So hang on a second. So it's the total number of these miles here. Okay, so now that I do, I'm going to click on it and elect, of course, to minimize it. Okay, the variables are the 0, 1 selections, the binary selections, okay, as well as use the control key, as well as all the customer assignments here. Okay, now the constraints. We'll start with the easy ones, right? The constraints are that each customer must be uniquely assigned to a single service center. So each of the customers must be assigned to a single service center, and okay, we must have exactly, not at most, but exactly 3 locations. I don't know if that's a parameter. Yep, it is up here. Okay. Now, the next set of constraints are the ones that I was discussing a little bit earlier, right? So each one of the customer assignment matrix rows. So I'm going to add a normal constraint. I'm going to scroll down rather as much as I can. So each constraint in the assignment row has to be less than or equal to um, the binary selection here, right? And if I wish there was some way to sort of copy that down. I don't think there is, so I'm going to have to add them one by one, which is not that difficult because there's not that many cities. So number 3 is Dallas, add number 4 is Denver, add number 5 is LA, add number 6 is Miami, add number 7 is New York, add number 8 is Phoenix, add number 9 is Pittsburgh, add number 10 is San Francisco, and finally number 11 is Seattle. Okay, so quite a bit of constraints, but all essentially of the same type. So we have the minimize the total distance as explained earlier, right, which is calculated by essentially multiplying the number of trips times the mileage between the service center and the customer or city that's being serviced by the service center. Okay, subject to, or rather by changing the variables, the 0 1s for the binaries, right, which I of course have to add. Okay, but not just those, also the entire assignment matrix is binary as well. Okay, then the sort of normal constraint or business constraint or logical constraint are that we must have exactly 3 service centers, and each service center has to be served by exactly one. I mean, each customer rather has to be served by exactly one service center. And then you have these sort of constraints here forcing the assignments to conform to the locations essentially. Okay, so I don't think we need to make the end constraints negative, but we have to choose the LP quadratic, and you'll see that Dallas, New York, and San Francisco is the optimal solution, right? Dallas, New York, and San Francisco, but it shows you exactly that that the constraints that each of the customers is served exactly by one service center. Just simply looking at the matrix, you'll notice that the Dallas, right, is served by itself, and Denver is also served by Dallas. Okay, Boston, Chicago, L.A. I'm sorry, Miami, not L.A. Miami, New York itself, and Pittsburgh are served by New York Service Center, and then finally, what do I got? I got LA, of course, Phoenix, San Francisco itself, and Seattle are served by San Francisco. Okay, so to understand that the service station would always serve itself, which is enforced by these these weird constraints here, think about the following. Okay, if I had if we were assigned Dallas, right? So if we reassigned Dallas from serving itself 0 to being served by, I don't know, let's say New York, or you can have San Francisco. Okay, obviously the number of miles, okay, would increase. clearly, right? Because the Dallas serving itself, right, contributes 0 to the total distance, but now being served from New York contributes 1,800, total miles, right, which obviously is suboptimal. So that's just never going to happen. Okay, so I'm going to save this, switch back to the presentation, and pause.